All right, are there any questions? So last time we were actually finishing up the chapter on classification, and later on I realized I just had one page left, okay. So this was actually the last page, all right. So let's just, to connect with the previous class, let's just go back a couple of slides, right. And so in bolstered resubstitution, right, that is based on the heuristic that relative to making an error, more confidence should be attributed to points far from the decision boundary than points near it. Okay, that means if something is very close to the decision boundary, you make a mistake, that's probably not as bad a mistake, right? If something is way in the interior and still you're making a mistake, right? So in order to capture that, you basically put some, region, right? What they call kernel around each point, right? So, although this is on the correct side, but if you put that kernel, you can see that associated with this point, because this point is so close to the decision boundary, you're getting some error of probability of misclassification, right? And the idea is basically you're going to sum over these errors. Like this point, it should have been on this side of the decision boundary. It's here. So, it's getting weighted by the weight of the kernel, right? And you have to be careful about how you choose the kernels and all that. And we have not covered this method in detail, right? So I'm not even going to try to, go over the text on the next page that is telling you about how to choose the kernels, okay? If you're interested, you can go and read Dr. Braganito's paper on this, okay? I mean, in fact, if somebody wants to, they could even present that, okay? Now that brings me to the topic of presentations. Have you guys chosen your papers or anything like that, or? Oh, I mean, you're quite relaxed, looks like, huh? Because in the past, I mean, my experience having people have come and bothered me, can I do this paper, when do we have to do that? The reason I'm saying is this time I'm going faster, okay? Because technology, right, all this business of, using screenshot and all that, I don't have to write on the board, right? So I don't have to erase, I don't have to move from one side to the other, right? So we are going faster, so we will finish faster, okay? I am on page, what is it? Is it like 540, right? Of the PowerPoint slides, and once we get to page 695, right, I'm done, right?
So are we going to get your permission on the paper, or we can choose
It's
from?
better if you get, yeah, because we don't want overlapping, right? We don't want the same paper to be presented by multiple people, right?
Okay.
So yeah, pick up a paper and yeah, permission not for doing quality control. Okay, I know that you're not going to take a term paper from grade 3 and come and present here. Okay, you're not going to do that, right? So I'm not trying to do quality control, but instead of having people wanting to present the same paper, right? We can probably avoid that if you show that to me. Okay, so now is the time for you to start looking, right? Go to the either the center website or the GSP Lab website, right? You don't have to pick it from there, but there are lots of papers over there on many different topics like classification, clustering, and so on, right? You're already getting a feel for the engineering techniques that are being used, okay, to analyze biological data, right, and to arrive at different conclusions, right? So you feel, and again, I mean, there are a lot of agri-life students here. If you want to, take the particular agri-life project that you're assigned on and, read some paper and present that, that's fine too, okay? It does not have to be, animal biology, it doesn't have to be cancer, right? It has to be basically, engineering applications in genomics, so some engineering stuff that is applied to a problem in genomics, right? So now is the time for you to start looking, right, for papers, right? Because my guess is that November 3rd we are going to have the second exam, right? I'm not going to be here, all right? Somebody else will come and proctor, right? So, but my guess is that after that, pretty soon we will start with the presentations, okay? And there are 17 people in this class. Even if 3 people present every class, we need what, like maybe 6 classes, all right? So that's 2 weeks we need just for presentation, huh?
I mean, three people in one class, so each people will have
15 to
around
20
10
minutes,
to
huh?
15 minutes.
Yeah. We could make it 20 minutes, but then we are going to stretch into the. Why you don't like it? That's how much time you will get at conferences to present, all right? If you're a big plenary speaker or something, then they might give you 1 hour, right? But you'll get 20 minutes, and usually it's 17 minutes for the presentation and 2-3 minutes for questions. Okay, so yeah, so make like 20. I mean, you have to focus on giving the big picture, right? Nobody wants to know every nitty-gritty detail that is there in the paper, right? I mean, if there is a reviewer, they might want to know, okay, when you're publishing the paper. But in general, for presentations, the big picture is more important. Okay. So yeah, start looking at papers, and deciding on something, because once the lecture stuff is over, we finish covering all the topics, right? Then it'll be our presentation, and we are done. Okay. In the meantime, there are homeworks associated with each of these topics, right? Like I gave you the homework associated with the ratio analysis paper, right? Right now, I can also assign a homework based on classification, because we're almost done with that chapter, right? Do you guys like doing those homeworks, or you don't want to do? Right? No, I'm just saying, because these homeworks were not designed for you. Okay, they were designed for undergrad students, all right? Because they were clueless. But I think it wouldn't hurt, and you're getting, it's like easy stuff. You get 20% probably, right? Instead of putting the whole weight on the final paper presentation, right? You can do some work, and if you don't know, it's not that difficult. So if you don't know, you can pick it up, right? If you know, you do some work and get some credit, right? I don't see anything wrong with that. Okay, this is the first time I put those in. Those undergrad homeworks. I thought I'll just give it to. I mean, for the undergrads, it's a problem, because some of these topics like classification and all that, right? When we talked about Bayes rule and all that, many of them have kind of been trying to graduate from undergrad school, and probably surely you know that better than any. They have tried to stay away from 303 and all that. Okay, and suddenly to see all these probabilities pop up over here, they can get really mad, right? So they were upset that I didn't put that as a prerequisite for the undergrad class and all that stuff. That's the main reason why this semester I'm not teaching it as a stacked class with 419, because for the undergrads they would just do the two tests and then these homeworks, right? While for the grad students it will be the two tests plus the paper presentation. Right? So I thought I probably need to think about it some, and get some input from people before offering it again to undergrads. The biology is no problem, because but when it gets to the stochastic stuff, then it becomes an issue for them. But you all agree that it's a good idea to do those homeworks, right? Or you're too busy, or huh?
You ask me?
Yeah. Because you're the person that has come here direct from undergrad class, right? I mean,
Oh,
no, it is a good idea, right? I mean, to do it. So
how many homeworks are we going to have?
we have 5 homeworks, like for each of the topics, right? Like,
Four.
okay. Or yeah, let me tell you the topics. Ratio analysis, you already did it, or you're doing it, right now. Then there's one homework on classification, right? Then there's one homework on clustering, right? Then there's one homework on expression prediction, and one on intervention and control. And I have to admit, probably the second last and the last homework, because one of my former PhD students, he created this, and you know how when you're a PhD student, you're working on something, you're really, really enthusiastic about that. So he probably made, and that's why some of those problems I didn't even assign to the undergrads. Like there might be 6 problems in there, okay, and it's not difficult, but it can be time consuming. So we will negotiate, okay. Right, let me assign, then after that we'll negotiate, right? No, because I mean, you guys didn't have any homework from the beginning of the semester, right? So suddenly at the end of the semester, I don't want to burden you with the paper presentation, right? And then a ton of homework, right? So it will not be a ton. I think it's only in the last homework, or maybe 1 or 2 problems that might take more time. And you can pick that up by doing courses like pattern recognition and all that. Those are not problems that are specific to this class or to genomic applications, right? So you can pick it up in another class if you take 649 or something like that. So we'll talk about that. Let's get to that homework, and if you're finding it too difficult, let me know. We'll just reduce the number of problems. Not on these, okay? Not on the ones that I already assigned. That one I want you to do, all right? And I will tell you, which one is negotiable and which one is not, okay? See, everybody is doing plea bargain and all that, so we can also negotiate here, right? Okay, so we are done with the chapter on classification, right? And we've looked at so many different issues about error estimation, the small sample problem and so on, okay? But again, the classification here, other than the sample size, it is no different than what your doctor is doing, okay? He or she is listening to your symptoms, all right? And based on that, they're trying to spit out a disease label, right? For what disease you have, right? And in the database, you basically have the probability of the symptoms given the disease. So it is basically a Bayesian classification problem, right? And here, of course, the challenges are a lot more, because you have many, many potential features, right? Thousands of them. So you have to figure out, which ones you're going to use, and also the sample sizes are very small compared to the number of features. Okay, and because in the biological community, like people don't have a very good appreciation for this, so sometimes they will publish papers that somebody with a background in statistics will think meaningless because the sample size is so small, right? And they have so many features, but they will write something and publish it, and it usually gets published, because you don't have the IEEE guys sitting over there. IEEE automatic controls people. Oh, this is already done in 1950. Throw it out. Okay, you probably don't have that, so because this is so new. Okay, so any questions on classification? And again, if you take a course on pattern recognition, they will spend a lot more time on each of these topics. Okay, I just gave you the big picture and the real fundamental concept. Okay, after that there are details. Okay, you can modify, look at properties of different methods and so on. Okay. The next topic that we are looking to look at is clustering, right? So in classification, basically you're trying to split stuff into different classes. Okay, you train a classifier, and then you want that when you give it a new sample, it should be able to correctly say to which class that new sample belongs, right? So in clustering, the problem is a little different. Okay, you have quite a bit of data that is thrown at you, and you want to basically group it into clusters. Okay, that's the idea. So a cluster operator will take a set of data points and it will partition the points into clusters or into subsets, right? And clustering has become a popular data analysis technique in genomic studies using gene expression microarrays, right? So time series clustering, say for example, you're looking at gene expression, okay, how it is varying across time, okay, which genes are going up and down together, right? If there are genes that are going up and down together, maybe they are controlled by a common switch, right? A common regulator, right? So similarity indicates, in time series clustering, possible similarity between genes indicates possible co-regulation, right? Another way to use gene expression data is to take the expression profiles over various tissue samples and then cluster these samples based on the expression levels for each sample, right? So you might find that, samples that come from similar cancers, right? There the genes behave in the same way, so you could group them together, right? So this approach offers the potential to discriminate between pathologies based on the differential patterns of gene expression, right? Now, clustering is not, as exact a science as classification. Okay, classification has got a very fundamental basis, right? Strong theoretical basis. Clustering is more like hand waving, right? So classification exhibits two fundamental characteristics, and we have already seen those. Number one, the classifier error can be estimated under the assumption that the sample data arise from an underlying feature label distribution, right? You can find out the probability of misclassification, that's the classifier error, right? Then the second thing is that if you have a family of classifiers, you can use sample data to learn the best classifier in the family. Okay, we've already talked about that. Okay, and you have results saying that if you have a large enough sample, you will ultimately approach the best base classifier. Right. So once you have designed a classifier, the classifier represents a mathematical model which provides a decision mechanism relative to real-world measurements. And the model is representing scientific knowledge to the extent that it has got the predictive capability. Because the classifier, when you give it a new sample, there's a good chance that if it's a properly designed classifier, that it will spit out the correct class label, right? And the purpose of testing or error estimation is to quantify the worth of the model, of this classification model that you have come up with. Now the problem with clustering is that it doesn't have any of these properties, right? So clustering has historically lacked both fundamental characteristics of classification. Right? Many validation techniques have been proposed for evaluating cluster results. And these are generally based on the degree to which the cluster derived from a set of sample data satisfies certain heuristic criterion. Right? And this is significantly different than classification, where the error of a classifier is given by the probability of an erroneous decision. Right? And the problem is illustrated in the following figure that, clustering is kind of subjective. So suppose somebody gave you all these points, okay, over here. So someone could come and say, okay, there are three groups here, three clusters, 1, 2, 3, right? Some other person might say, well, all of this is one cluster and this is another, right? So who's correct? Okay, we don't know. Right? So in that picture, both the cluster results appear to be reasonable, but the performance of a clustering algorithm cannot be measured by observing the results of a single application. Rather, as with classification, its performance must be measured relative to predictive results on a distribution. Right? And for clustering, error estimation must assume that clusters resulting from a cluster algorithm can be compared to the correct clusters for the data set in the context of a probability distribution, thereby providing an error measure. Right? And the key to a general probabilistic theory of clustering, including both error estimation and learning, is to recognize that classification theory is based on operators on random variables, whereas the theory of clustering needs to be based on operators on random sets. Right? So Professor Doherty here has some papers on these random sets and all that, and apparently those are pretty difficult, right? I mean, even these are pretty difficult mathematical concepts, but if you're interested, you can go and take a look, right? I mean, that's probably one of the reasons why clustering is not an exact science. Okay, it's like more hand waving, right? You do on an ad hoc way, but you know, your PhD students here, and if you're interested in working on that, you know, by all means, you know, there are some papers that he has written where he talks about all these random sets and all that, you know, but we are not going to get into that because, again, I mean, we are covering a lot of territory in this course, all right, and our goal is to get the big picture, all right, to have a working knowledge everywhere, and then if somebody wants to, let them go and worry about random sets, you know. So instead of getting into the theory of all those random, because that'll probably take the whole semester to do, right? And even I'm not familiar with that. We are just going to look at some standard clustering algorithms, right, that are popularly used. Just like we looked at classification rules in the last chapter, like LDA, QDA, and then support vector machine and so on. Okay, here we'll look at some of the clustering algorithms that will be covered in any standard course on pattern recognition. Right? I believe it will be covered in 649 next semester, right, if you're taking that class. So let's look at examples of clustering algorithms. Right. So here you basically have a bunch of points and you're trying to group it into different clusters. Right. You're trying to create clusters by grouping those points, okay, into individual clusters. So if we envision that there are clusters formed by points X generated by a random sample S from a mixture of M circular Gaussian conditional distribution. So let's assume that there are M different classes here, right? M different clusters. So then you have to define what are called the centroids. Okay, for each cluster you'll think of a centroid. Okay, and what is the centroid? The centroid for each cluster will be defined in such a way that this quantity is minimized. Right, and let me try to explain what this is. Okay, now for each point, okay, each sample that you pick up, all right. Let's say you have you have M different clusters. Okay, which have M different centroids. Okay, so let A1, A0, A1, A2 up to AM minus 1 be those centroids. Okay. So for each point in the sample, all right, you're going to take the Euclidean distance from each of the centroids. Okay. And you're going to put that point in the cluster for which you get the minimum distance from the centroid. Okay. So here you minimize overall j greater than or equal to 0 less than or equal to m minus 1. That means over all the possible clusters, the distance from the point to the centroid, right, square of that. Minimize that. Okay. So, and then you sum this distance, right, over all the points in the sample, okay, and then divide it by the number of points in the samples. That's the cardinality of the set S, okay. So this is, so now you want to choose the centroids in such a way such that this total distance, right, like the sum of the distances of each of the points, okay, from the nearest centroids, right, that is the average sum is minimized. Okay, that's a good way to pick the centroids. Okay, what is the choice of the centroids such that this whole thing is minimized? Okay, so this seems to be a reasonable choice for the centroids of the M classes arising from the conditional distributions. Okay, once you have found out the centroid, then for each point, all right, each point in the data set, that point will belong to the cluster whose centroid is the closest. Okay, and this actually breaks up this space using what are called Voronoi diagrams, right? Like if you have, you know, like if these are the centroids, all right, then you'll draw this kind of line, okay? Then this kind of line right here. So if this point is closer to this, then it'll go to this cluster. Okay, so that's called a Voronoi partition, right? So let V, so these M clusters will create a Voronoi partition of the d-dimensional space, right? So V1 through Vm be the Voronoi partition of Rd induced by these centroids, A0s, A1s, Am minus 1s. A point is going to lie in a particular component of the Voronoi partition, right, in Vk, if its distance to Ak S, that means to that kth centroid is no more than its distance to any of other of the different centroids. Okay, so this is the idea. Like if you have a point in here, it's lying closest to this centroid, so it will go into this cluster, right? So that's the idea. So for Euclidean distance clustering, the sample points will be clustered according to how they fall into the Voronoi partition, right? Now finding these guys, okay, it's easy to, this is one of those problems that's easy to define, okay, to state, but hard to solve, okay. We're saying that, okay, those centroids, they are going to be those locations that are going to minimize this value, right? But how are you going to find those centroids? Okay, that's the question, right? So, and it's not easy. This problem is hard to solve, right? So, to find those centroids, you can use some iterative algorithms, right? And that algorithm, one of the algorithms that is used is called the k-means algorithm. So direct implementation of Euclidean distance clustering is computationally prohibitive. Right? You can see because you don't know the answer, you're going to pick this and then you're going to find out that the sum of all those distances is going to be minimized. Not easy. Right? So a classical iterative approximation is given by what is called the k-means algorithm, where k refers to the number. Sometimes you'll see it referred to also as the c-means, okay, depending on how many clusters you have. Right? So where k refers to the number of clusters provided by the algorithm. So here you're going to update the means. The mean is like the centroid of each of the clusters, right? So each sample point is going to be placed into a unique cluster during each iteration, and the means are going to be updated based on the classified samples, right? So you start with some guess for the means, right? Then you will get a Voronoi partition corresponding to that, cluster everything, then again go ahead and compute the mean of each of these clusters, okay? Repeat the procedure, right, with all the data points, right? So given a sample S with n points to be placed into k clusters, initialize the algorithm with k-means, m1, m2 up to mk among these points. Now then for each point x in S, right, in the sample, calculate the distance between x and each of these means, right? For I equal to 1 to up to k, form clusters C1 through Ck by placing x into Ci if the distance from the corresponding mean is less than or equal to the distance from all the other means, right? And then once you've gotten new cluster, go ahead and compute its mean, right? Like the center of gravity or whatever, go ahead and compute that, and then repeat the procedure until the means don't change that much. Okay, this is called the k-means algorithm, right? And it is used quite a bit. So at each stage of the algorithm, the clusters are determined by the Voronoi partition associated with the means that you have at that stage, m1, m2 all the way up to mk. Right. Now two evident problems with the k-means algorithm are, number one, you have to know how many classes you're going to have. Okay, so the prior assumption on the number of means that you're going to have, and the second thing is the choice of the means to seed the algorithm. Okay, what is the initial choice of the mean going to be? Which points are you going to pick as the means initially? All right. So these are two things for which you don't have any definite guidelines. Now to get around this problem, you can use what is called the fuzzy k-means algorithm, right? And I'll try to explain. All right, before that, any questions on the k-means algorithm? Any question on whatever clustering we have discussed so far? Again, I'm trying to give you the big picture, idea about what exactly is involved, right? Now, the equation that we had earlier, okay, for that distance from the centroids, okay, a couple of slides ago, right? This thing here, okay, I can write it a little bit differently. See here, what I'm doing is I'm taking the minimum distance, right? I mean, I'm saying that for x, okay, I'm trying to find out the centroid that is closest to it, and I'm taking the distance from that centroid, okay? In fuzzy k-means, I'll do something slightly different. So here the underlying assumption is that x can belong to only one of the clusters, okay? In fuzzy k-means, I will say that it can belong to each of the clusters with a certain probability, right? Here, also it can belong to each of the clusters, but the probability of belonging to one cluster is just 1. Okay, that's the difference, right? So if I make that change, then I can actually write these terms without taking the minimum. Okay, I can take the distances from the individual centroids, right? And I can weight them by the corresponding probability, right? So that's how this expression is going to be rewritten on the a couple of slides later, right? So see, equation 1, can be rewritten like this, right? So here this is the same distance, xi minus aj, right? The distance of the ith data point from the jth, the centroid of the jth cluster, right? I squared this distance, and then I multiply this by the probability, right? The conditional probability of Cj given xi, which is basically the probability that xi, the ith data point, belongs to the jth cluster, right? And then I take it to some power b. B is the design parameter, right? And then I sum over j going from 0 to m minus 1. Look, what happens in the earlier case? In the earlier case, the probability of Cj condition on xi is going to be 1, right? Except for a particular j, right? So only that term will survive, and that is the one that is going to give you that minimum distance, right? That's why we didn't have two summations over there, okay? Here we got two summations, right? So is everybody convinced that the earlier sum we can rewrite it like this? Any questions on that? So where probability of Cj condition and xi is the probability that the ith data point is going to belong to the jth cluster, which is either 0 or 1, and is 1 only for the minimizing j of equation 1. Okay. But now we are going to make the assumption that this single point, it can belong to different clusters with different probabilities, right? So a fuzzy approach results from letting the conditional probabilities reflect uncertainty so that cluster inclusion is not crisp, and letting b greater than 0 be some parameter affecting the degree to which a point can belong to more than a single cluster, right? And the conditional probabilities, of course, they are probabilities. So if you're looking over all j's, right, probability that xi belongs to Cj, if you look over all the possible classes, all right, all the possible clusters, that should sum to 1. Okay. So now, so for fuzzy k-means, okay, what is the problem? I will try to minimize this guy. Okay, remember you are trying to choose the centroids, okay, to minimize that distance function, right? I'll try to minimize subject to this constraint, right? Because these conditional probabilities have to sum up to 1. Okay. So how would you solve that problem? You're trying to minimize something subject to a constraint, right? What method are you going to use? Anybody? Yeah. You're going to use the method of Lagrange multipliers, right? And that would, if you took the course 649, right, the pattern recognition course, they probably will ask you to do that exercise, okay? So so let P sub j denote the prior probability of the jth cluster. Since the conditional probability that xi and cj are not estimable and are heuristically set, we view them as fuzzy membership functions. So in this case, for minimizing the values of that distance function, the partial derivatives with respect to aj, that is the centroids, and with pi, they will satisfy these relationships, all right? And you use the method of Lagrange multipliers, all right? And you solve, you will get these update equations for the mean and for this conditional probability, right? So, so first, let's say if you're given these conditional probabilities, probability of Cj condition on xi, you'll use that, okay, and the sample data that you have to determine the mean. In the next step, you now have the mean, you have the sample data, you'll use that to update the conditional probability, right? So go back and forth, all right, until these things don't move anymore. Okay, that's how the fuzzy k-means algorithm operates. So these lead to those two equations lead to the fuzzy k-means iterative algorithm. So you have to initialize the algorithm with the parameter b, right? That's the power to which that conditional probability is being raised. Then with the k-means, m1, m2 up to mk, and also the membership functions, the probability that the ith data point belongs to the jth cluster, right? And where, of course, the membership functions have to be normalized so that their sum is 1 for any fixed xi, right? Then you will recompute mj and probability of cj condition on xi using those previous two equations, and you'll repeat until there are only small pre-specified changes in the means and in the membership functions, okay, until you basically converge, right? It's not guaranteed to converge, but apparently it works well most of the time, okay, and people use it. So the intent of fuzzifying the k-means algorithm is to keep the means from getting stuck during the iterative procedure. All right, any questions on the fuzzy means iterative algorithm? So we did k-means, we did the fuzzy k-means, right? Now, The next clustering algorithm, right, which we will not discuss in detail, these are called self-organizing maps, all right. Again, here it's just a different way of coming up, of updating the means, right. And it requires a little bit more mathematics, but even then it's not very rigorous, okay. It's not founded in solid theory, right. So I mean, and it would take more time, but let me just quickly go over it, you know, at least parts of it. So self-organizing maps provide a different extension of the k-means concept. The idea is to map high-dimensional vectors in Euclidean space to a low-dimensional grid in a neighborhood-preserving manner, whereby we mean that vectors which are close in the high-dimensional space have got close representation in the low-dimensional grid. Right? And to describe self-organizing maps, you have to start with an ordered lattice and then define a neighborhood function. And let's not worry about all of this stuff because, you know, at the end of the day, you know, it's basically the same kind of algorithm like the fuzzy k-means, right? You basically you have the centroids, right, or the means, and you have to update them, okay? Except here the update will take place according to a slightly different equation, right? See, the update will take place like this, right? So the vector m of t is then updated according to this, where the neighborhood function will come into the picture. Here is the deviation between x, right, the sample point, and the ith mean, right? That gets weighted by some by some neighborhood function with some properties that it has, okay? And I don't want to, you know, confuse people about all these different properties. If you have the time, you can look at it. But again, this is also standard stuff, right? You will see on any book on pattern recognition, right? Like, and the book that I was talking about was Duda and Hart, right? So you guys said Bishop or something, but I don't know. Here they use that book, Duda and Hart, right? So the vector m, that means, you know, the centroid, okay? Vector, the different components will be the centroids of the different clusters, right? So the vector m is updated in this fashion, right? And a critical role is played by the neighborhood function in achieving the preservation of neighborhood relations. This algorithm is also very popular and used for various purposes. However, many theoretical questions remain regarding the organizational nature of the algorithm and convergence, right? And once you have these points, right, this M1, M2 up to MK, right, you basically have these centroids then, right, and you you cluster according to the Voronoi partition, right. So this is just a different algorithm for the evolution of the centroids, okay, or the iterative evolution of the centroids. All right, any questions? Now both k-means and fuzzy k-means are based on Euclidean clustering, Euclidean distance clustering. Another approach is to iteratively join clusters according to a similarity measure, right? And that is called hierarchical clustering. So the general hierarchical clustering algorithm is given by the following procedure. First, you'll initialize the clusters, Cj. You might even say that each point is a cluster, right? And then you will start grouping things together. Similar points, you'll put them in the same cluster, right? So initialize the clusters by Ci equals the individual points and by a desired number, final number k of clusters. How many clusters do you want, right? So proceed to iteratively merge the nearest clusters, nearest in terms of some distance function, okay, according to the similarity measure until there are only k clusters. Another approach might be to continue to merge until the similarity measure satisfies some criterion, right? And the merging process can be pictorially represented in the form of what is called a dendrogram, where joined arcs represent the merging of different clusters, right? And as already stated, the hierarchical clustering is agglomerative, right? In the sense that points are agglomerated into growing clusters. So initially you start with individual points and then you group together, right? So it's accumulating, right? It's agglomerative. You could also have the reverse, okay? You could start on one big thing, right? And then start breaking it up, right, into clusters, right? You could do that too. So one can also consider divisive clustering, in which beginning with a single cluster, the algorithm will proceed to iteratively split the clusters. Now various similarity measures have been proposed, okay, for checking similarity between clusters. Three popular ones are the minimum, maximum and average measures given by. So the minimum measure, the distance between two clusters Ci and Cj, will be basically the minimum, all right, will be the distance between the two closest points in the two clusters. Okay, so you look over cluster Ci, look over cluster Cj, all right? Find the minimum distance between a point in cluster Ci and a point in cluster Cj, right? So that is the minimum measure. Another one might be the maximum measure, right? So the distance between the two clusters is measured by the maximum separation between two elements, right? So you look over elements in Ci, in the first cluster, elements in the second cluster, and the distance between the two of them is the separation between the farthest elements in the two clusters, right? Yet another, and again, these are all ad hoc measures, right? There's no big theory. Maybe there is theory that, some of you guys will work it out and write a paper and discover, but at this point in time there is not, okay? So the other one is the average distance, where basically the distance between these two clusters, C sub I, C sub j, is the average. So you sum the distance between each pair of points, right, coming from the two different clusters, right? Take these points pairwise, sum the distance, average it out, because there are cardinality of Ci times cardinality of Cj points altogether. Average it. That's the average distance or the average measure. Now, again, I mean, when you're doing hierarchical clustering, you're grouping things together, right? If you're doing hierarchical clustering using the minimum distance, then that is called the nearest neighbor clustering, right? This is just terminology, right? Because the minimum distance is actually taking the nearest distance between the nearest neighbors into account. If this clustering halts when the distance between the nearest clusters exceeds a pre-specified threshold, right? That means if the distance between these clusters is more than something, you say, okay, I cannot group the two of them together, so the clustering stops. Then this is called a single linkage clustering. Now, given a set of clusters at any stage of the algorithm, it merges the clusters possessing the nearest points, right? Now, if we view the points as the nodes of a graph, then when two clusters are merged, an edge is placed between the nearest nodes in the two clusters. Hence, there are no closed loops created, and the resulting graph is a tree. And if the algorithm is not stopped until there is a single cluster, the result is a spanning tree, and the spanning tree is minimal. Don't worry about all this stuff, because this is about graph theory. Okay, it's not even relevant to what we are covering here, right? Now, while this algorithm, this business of clustering things together, right, uh, is intuitively pleasing owing to the manner in which it generates a hierarchical subcluster structure based on nearest neighbors, it is extremely sensitive to noise and can produce strange results such as elongated clusters. And it is also very sensitive to early merging, since once joined, points cannot be separated, right? So in this technique, you basically merging clusters together. Once they are merged, that is it. Okay, you don't go back and split them up again, right? So there are variations of this, where probably people might merge, then go back and do and all that, but we're not covering that here. So we talked about the nearest neighbor clustering. Then the farthest neighbor clustering results from using the maximum distance. I gave you three measures, right? I mean, the minimum distance, the maximum distance, the average distance between cluster. All right, for the distance between two clusters could be measured by the minimum distance, right, between the points in the two different clusters, the maximum distance, or by the average distance, right? So if you're doing the clustering based on maximum distance, then you get what is called farthest neighbor clustering. And if it halts when the distance between the nearest clusters exceeds a pre-specified threshold, then it is called a complete linkage clustering, right? And given a set of clusters at any stage of the algorithm, it merges the clusters for which the greatest distance between points in the two clusters is minimized. And this approach counteracts the tendency toward elongation from which the nearest neighbor clustering suffers. And finally, if the algorithm halts when the average distance between nearest clusters exceeds a pre-specified threshold, then it is called average linkage clustering, right? Again, no surprises here, okay? Complete linkage clustering, right? Average linkage clustering, and single linkage clustering, right? Now, all right, any questions so far? So this is an example of, clustering algorithm, right? That is applied to cancer data, okay? So here you have tumor tissue. This is one type of leukemia, MCL, right? And that other one, DL, BCL is another type of leukemia, right? And these are the genes, okay? Along the vertical direction, these are the genes, I think 23 or 24 genes, okay? And these are all the samples that are there, okay? And you can use hierarchical clustering, like you're grouping things together, and this is the dendrogram, right? put these two together, then merge this and so on. Okay. So this shows a sample of 30 patients, which are the columns, all right? These are the different tumors for 30 patients suffering from B-cell lymphoma, that's BCL, and the expression profiles, rows of 24 genes. There are 24 genes in here across the sample. The samples have been hierarchically clustered, and the clusters correspond perfectly to two types of lymphoma, DLBCL and MCL. So all the green ones, these are all DLBCL, and this is the MCL. Right? They're separated out. And you can see, right, then among these genes also, right, these genes seem to behave, right, differently across these two different types of cancers. Like you're seeing these genes more or less are red, right, in here, right, and they're green in here, okay. So you may be, you might be able to pick one gene in this group, right, and maybe one gene in here, okay, because it's representative of the whole class, right, and use that to, differentiate between which cancer you're looking at if you're going to do the classification. So the genes have also been hierarchically clustered, and it appears from the figure that the red label genes are upregulated for MCL and the downregulated for DLBCL, right? Whereas the green label genes are upregulated for DLBCL and downregulated for MCL, right? Whether it's upregulated or downregulated depends on whether it's colored green or red, okay? So thus the different gene clusters seem to classify the lymphomas, right? More precisely, the clustering might provide feature selection, right? Because you have so many genes, you don't know which ones to use. Maybe you pick one, right, from the red, right, and one from the green, right, and that'll do the job. So more precisely, the clustering might provide feature selection in the sense that actual classification might be accomplished by a two-gene feature set, one red labeled and one green labeled. So you might be able to just pick one of these genes from here and one of these genes from here, and you have your classifier. Right? You don't need all the genes. And I think this is from a paper that appeared in Nature maybe 10 or 12 years ago. Right? Those were the days when people just started doing classification and clustering in the context of gene expression. All right, any questions? Now, a clustering algorithm will operate on the point set as a whole by partitioning it, right? Because you're going to break it up into different clusters. So its error is based on the accuracy of the partition. Essentially, if we assume that the points come from different distributions, label them accordingly, and match the results from the clustering algorithm with the subsets of the partition in the best way possible, then the error is the number of mismatches, okay? Your clustering error. Now, this idea can be formalized in the probabilistic theory of random sets, which we are not going to do here, okay? Instead, we are just going to give you some heuristic criteria for evaluating the performance of a clustering algorithm, right? Which is there in basically most textbooks on pattern recognition, right? So the error of a cluster operator can be defined in the context of random point sets in a manner analogous to classification error. One might loosely define a valid cluster operator as one possessing small error, or even more loosely as one that produces good clusters. Such a definition is vacuous unless it is supported by a definition of goodness. If one tries to evaluate a cluster operator in the absence of a probability distribution, that is a label point process, then measures of validity goodness need to be defined, right? They will not apply to the cluster operator as an operator on random sets, but will depend on heuristic criteria. That's what we are going to talk about. And their relationship to future application of the operator will not be understood, for the whole notion of prediction depends on the existence of a random process. So nevertheless, a heuristic criterion can serve to give some indication of how the cluster operator is performing on the data at hand relative to some criterion. So we will consider some methods that address the validity of a clustering output or compare clustering outputs based on heuristic criteria. These can be roughly divided into two categories. Internal validation methods will evaluate the resulting clusters just based on the data. External validation methods will evaluate the resulting clusters based on pre-specified information. Right? If somebody tells you that this has to belong to that cluster, you can use that. Okay. So external validation involves a criterion based on the comparison of the clusters produced by the algorithm and a partition chosen by some other means, say one produced by the investigator's understanding of the data, right? Let's say you know that this is one type of cancer, it has to cluster this way. Another one is a different cluster, right? So one criterion for this external validation could be simply the number of mismatches, which provides an empirical error. Okay, how many mistakes is it making? You know that these points should belong to the same class. Okay, let's say this pair of points should belong to the same class, but you find that your clustering algorithm is putting them in different classes. That's a mistake. All right, so you can kind of count those kind of mistakes. All right. So, and let me skip this part. This is again talking about, let's see. Yes. So let's just skip this part. Let's not worry about all these random sets and doing the theory right. Okay. Let's just look at practically how people evaluate the, performance of a clustering algorithm. Right. So suppose P sub S, right, and P sub zeta are the heuristic and zeta partitions respectively. So you have a clustering algorithm that's producing a partitioning, right? Bunch of clusters, and you also have something that is produced based on heuristics, right? So now we go ahead and define four quantities, okay? A is the number of pairs of points in the sample such that the pair belongs to the same class in both the partitions, the partition produced by the algorithm and the heuristic partition that you have. Okay, somebody else has given it to you. All right. B is the number of pairs of points such that the pair belongs to the same class in PS in one of the classes and in different class in P zeta. Right. C is the number of pairs such that the pair belongs to different classes in one of those partitions and in the same class in the other one. And D is the number of pairs in S such that the pair belongs to different classes in P sub S and different classes in P zeta. Okay. So ideally, if the heuristic one is correct, right, and your algorithm is good, then when 2 points they belong to the same cluster here, they should also belong to the same cluster in the other one, right? So ideally, if the partitions match exactly, then all pairs are either in A or in D. Okay, A because the same pair of points will belong to the same cluster in both the partitions, right? Or in D, or they'll belong to different clusters. But in reality, you will get something in B and C also. Okay, so you can go ahead and define an index of performance, which is called the RAND index. Okay, the RAND index is defined like this: A plus D over A plus B plus C plus D. Right? If the clustering algorithm and the heuristic partitioning they perfectly agree, then B and C are going to be 0. Right? Everything will be counted either as A or D, and you will get 1. The RAND index will be 1. So the RAND index lies between 0 and 1, and numerous external validation procedures have been proposed. Right? Now, internal validation methods evaluate the clusters based solely on the data without external information, and typically a heuristic measure is defined to indicate the goodness of the clustering. Right? So it is important to keep in mind that the measure applies only to the data at hand and therefore is not predictive of the worth of a clustering algorithm, even with respect to the measure itself. So a common heuristic for spatial clustering is that if the algorithm produces tight clusters, okay, tight clusters and cleanly, because you're trying to group things together, okay. If you have tight groups that are widely separated from each other, then you have done a good job, okay. That's a heuristic that you can use, all right. So you can, based on this, you can come up with a number of indices, right. And for example, so if you have a partition S1 through Sm, let that be a partition of the set S, right? And let delta between Si and Sj, right, be a between cluster distance. And sigma Si be a measure of cluster dispersion. That's the spread of each cluster, right? So if it's going to be good clustering, okay, and this one again, there is no reference. You're not doing it with reference to anything. There is no heuristic cluster that's given to you. Just looking at the data, okay, are the clusters widely separated, right, and are they tight clusters? Okay, so for that you can put in some measures. One of them is the Davis-Bouldin index, all right, that is defined in this fashion. And again, you can see if you have a tight cluster, all right, if you have a tight cluster, then this spread will be small, right? I mean, the dispersion will be small. This will be small, this will be small. Whereas that one will be large because the clusters are going to be widely separated. Okay, tight clusters but widely separated. So that means a small value for this index, right, will indicate good clustering, right? Because the numerator is going to be small, the denominator is going to be large. Similarly, the Dunn index is defined in this fashion, right? Again, here you want this guy to be small, right? I mean, because the clusters should be tight, right? So the spread in the cluster should be small, and the intercluster distance should be large, right? So this index you will want it to be large to get good clustering. So low and high values are favorable for alpha p and beta p respectively. That's what I tried to argue. And as defined, these indices leave open the distance and dispersion measures, and different ones have been employed. Yeah, I think we probably need to, yeah, we need to stop for today. Okay, but I'll finish off clustering next time.